that, and now I will be focusing on different pieces. So this is, well, as part of my job and the job of the other colleagues, what we do is we work on architectural patterns for customers and partners. And a lot of these are published on GitHub or on our, anyway, public on the public. This one is a blueprint or a pattern that is available as Terraform on the web. So let me start by highlighting a few things. So the goal of this pattern is to deploy LLM in a scalable way with observability on Kubernetes. The cluster is EKS, Amazon EKS. But because EKS is upward compatible, you could take the Terraform and manipulate it, hopefully just a little bit, and run it wherever you want. So now, how this is working is that we have on this side we have a group of what are called core node groups, which the Terraform pattern boots as first, because this one and it is a managed node group. So in AWS terminology, an autoscaling group. So this is fixed. It's something, a group of nodes that is there to host the core components of the cluster. And these are basically the critical add-ons that you well know, CSA driver, core DNS, and so on. This other one is created for the workloads. So in here, the base, and in here, the expansion. How that is instantiated, that part of the data plane is instantiated is through Karpenter. Karpenter, for those that don't know it, is an alternative cluster autoscaler. Its main purpose is to avoid creating managed node groups for allocating additional capacity. The downside of having managed node groups is that they need to be kind of consistent in the instance types in terms of CPU and memory. So if you want to have multiple instance types, you need to have multiple managed node groups. The benefit of Karpenter is that it talks directly to the EC2 Fleet API in the case of AWS. But again, it's open source and it's supported by other cloud vendors. So it talks directly to the EC2 Fleet API and basically requests, give me this instance, just one of this type. Okay? And it does that through a couple of custom resources. The node class, which includes the definition, for example, of the AMI, stands for Amazon Machine Image, so basically the operating system that is starting, subnet, security group, and so on. The other one is the node pool. The node pool includes a lot of interesting stuff, like the instance family, and in here we can see, this is a snippet taken from the Terraform that I mentioned. So instance family, G5 is a instance type in AWS that corresponds to GPUs, okay? Very general. And then we have these sizes. So of this kind of instance, I want you to consider these sizes. So this is a message from us, or a blueprint from our side, from the side of the administrator, to Karpenter. Karpenter reads this and then takes decisions. In this case, we have taints. Taints because we don't want unwanted workload to finish into expensive stuff like the GPUs. So we taint the nodes. And then in here we can define other stuff like, for example, spotting on event, in the case of AWS, but then you can define other stuff for other environments. The advantage of Karpenter is that also it can look continuously at the state of the cluster, look at the workloads, and put in place disruption if needed, which means if I am using my capacity, so my data plane is fully functioning and fully occupied by pods, all good. Otherwise, if Karpenter sees that, for example, we have two nodes that can be one removed and the pods moved to the other one, then it takes that decision and it does it. Or, for example, if it sees that the capacity can be changed in a way that you can save money, so optimize your costs, it replaces the nodes with a lower number, possibly, or different sizes, depending exactly on these parameters. This is for data plane, so capacity scaling. We'll look at the workload scaling in a minute. So I was saying that Karpenter, basically, whenever we then spin up our pods, which in this case are Triton Server pods, and I'm going to talk about that in a minute, it sees that these pods will be pending because they need, and this is how we use pod placement controls, so defining the labels, here, node selector and tolerations. So Karpenter, because of this, the newly launched Triton Server pods will not be able to run here because they want this kind of nodes. So, because they are pending and because Karpenter makes its calculations, it will spin up a new node enough to host this pod. So, a few words on Triton Server. So, we are using the Triton Inference Server to run our models. The Inference Server is basically a server, a wrapper that runs multiple frameworks, like, for example, TensorFlow or PyTorch. It can run multiple of those in parallel. They are called backends. So it has multiple backends. You can also build your own backend for Triton. Triton is also open sourced from NVIDIA. It runs not only on GPUs but also on CPUs and other architectures, like, for example, Graviton, so ARM-based CPUs, or also other instances of type, for example, inferentia and training, which are from AWS. So what the way it works is that I was saying it hosts multiple backends, which are frameworks like PyTorch and TensorFlow, and it pulls from externally or from a local directory the models. In here, for example, in the case of the blueprint, we are using VLLM as a backend. What is interesting is the way that the Triton uses the GPU in a to support concurrency. So Triton uses CUDA streams to support concurrency, which means that it can run on a single GPU or multiple GPUs, multiple frameworks, multiple models, and multiple instances of the model, of the same model. So that, for example, for every environment, or let's call it a instance of the model, okay, it has different queues which serve different inference requests. So they come in, and then the requests are they are manipulated and they are interpreted in a way that a sequence of instructions are created. These instructions, by definition, they need to be sequential. So these set of instructions, each one goes into a CUDA stream. But the hardware scheduler here can handle multiple CUDA streams and basically multiplex them so that the GPU power can be used most efficiently. There are other ways of managing concurrency on the GPUs. You might have come across those, like time slicing and the mix, so multi-instance GPUs. So the time slicing is similar to the CPU time slicing. You are allocating space and dedicating the time slices to every, for example, in this case, could be an execution of a single model, a workload in general. And with MIG, instead, the GPU is actually physically divided. So from a security perspective, the MIG is depending also on the on what you want to achieve, on your constraints. In any case, it's let's say a safer option because also it is physically divided into a separate GPU. So this is to explain what's happening inside here. Of course, there are other components like the NVIDIA device plugin, which makes available the GPUs to the workloads, to the pods, in these set of nodes. But in any case, so this is how the core of our pod and the container running inside it works. So we have this Triton Server that is using a VLLM backend and is serving our Triton, our model. So I was saying before that it pools the models, so it can use local storage in the repository in the blueprint. We are using S3, so an external storage. It supports other types of external storage. And what you do here is basically you build this kind of structure. So you have like a folder structure, like you have the models, you have the model name, the version, the model itself, and then you have a configuration file. I'll show you in a minute a couple of things about the configuration file. So you see you can have multiple of these, which are related to multiple models, And in here, you define also what kind of framework that will be running. Just to complete before I move on, in this specific case, the VLLM backend is actually pulling from here then the model from Hugging Face. Okay, so just a couple of things in relation to how the Triton uses the GPU in relation to the instances of the model. So in here, instance is related to the instance of the model. Like I said, Triton can run multiple, for example, multiple instances of this LLM model, whatever that we are using. So you can also define, by default, it runs just one model instance. So all the requests will go to that model instance. If you want to run multiple of those, because you want to run them in parallel and serve them in parallel, you can also increase the number of the instances. For example, this way, by selecting, I want on GPU number 0, I want one instance of the model, and I want an additional 2 into GPU number 1 and GPU number 2. It also supports dynamic batching. So the dynamic batching of the requests is basically groups. Like, you know, GPUs work well with parallel stuff. So by grouping together multiple requests and feeding the GPU with multiple requests, you are achieving a higher efficiency. So there are a number of parameters. All of this is in the config file that I mentioned before, which is inside the folder structure. So this is to give you a little bit of a picture of how what we are running and how we are running it. Now, going back to the scalability thing. So Karpenter is addressing data plane scalability, so capacity scalability. Before that, of course, we needed to look at the workload scalability. So we want to look at this pod and see when it requires scalability. So in order to do that, Triton by itself exposes a few metrics, Prometheus metrics. This is one of those that we are taking and using on a horizontal pod autoscaler. It's the time that a request spends in the queue, which I was showing you earlier here. Okay. So I was saying that Triton exposes this metric, and we have deployed a KubeConEU stack in there, which includes Prometheus, Grafana, and also we have the Prometheus Adapter. The Prometheus Adapter is basically registering the custom metrics API, the metric that I mentioned. It's a little bit modified in order to, this is basically the, instead of using microseconds, because there, it's exposed as milliseconds. So it's a little bit of elaboration, but it doesn't change much. So Prometheus Adapter is exposing this metric as to the HPA. And here we have in the HPA horizontal pod autoscaler, we track the metric and we scale replicas between them. So whenever the queue becomes, well, requests start to spend longer time within the queue, and the time here is set in, I think it's in 10 milliseconds. That's the threshold above which then HPA starts scaling from 1 up to 5. So this is more or less the what's happening. Just maybe a few words on Karpenter, how it actually very quickly how it works from an evolution of the requests perspective. So it first creates a node claim, and the node claim is the custom resource that represents a request for a new node to the cloud provider. The node claim can be in different states, launched, registered, initialized already, and the sequence is explained in here. So first is created, then it is requested, and it is launched, and then when the node is ready, it needs to register with the cluster to be part of the cluster and not just external. Now, like I was saying before, and what generally is experienced is that because we need to download to pull container images, for example, Triton container image, or the container image of the backend that is running basically the workloads. We also need to pull the images and the models, and all of this is kind of heavy. So a few ideas or recommendations that we provide and we use for faster startup are these ones. So first of all, you could use a Sochi, which is seekable OCR. This again is another open source project alternative started by AWS, but again open source. It basically creates a separate index of the container, of the layers within the container, and then you need to use a alternative snapshotter, which is replacing generally the overlay FS, which is the container, these snapshotter. The way it works is that, so the objective is, I don't want to download the full container before starting and running it. I will use the fundamental layers, start the container, and then keep pulling. It's a technique that is used in other contexts as well. Again, you need an index artifact because it lists the layers, highlights the ones that are fundamental, basic, and the other ones. And then also you need the snapshotter, which is able to read the artifact, the index, and decide what to do. Multi-stage builds, again, you might have come across this in the Docker file. You just define different froms to reduce the size of your image. The last one is based on the BottleRocket operating system, another open source project. BottleRocket, for those that don't know it, is a operating system based on Linux, minimal, with the objective only to run containers. So everything is stripped out, like packages, interpreters, the shell itself. There's just what needs to be part of a Kubernetes cluster and being able to run a container. There are some security features and so on. I'm not going to go into that right now, but there is an important aspect which is useful. It uses two different volumes, one for the operating system and one for the data. So what you can do is offline, start it, The data will be in here, so everything that you put into the data volume. You take a snapshot, for example, in this case, in our case, it's on EBS. Snapshot goes S3, and when you run, now, offline stops here. Now, when you run your cluster in Karpenter, you define this. So you select that block device mappings. So you tell in the node class custom resource, where you define some properties of your nodes, you basically tell Karpenter that to pull from S3 the snapshot and fill in the data volume with that one. Okay, I think I provided an overview of all of it. Maybe I can show you just very briefly. This kind of snapshot that I took just a few days ago, and where you can see the spikes, basically in the metric that I was mentioning earlier. And this is the threshold, actually, at 10. This is logarithmic. And wherever there are the spikes of the metric, you can see that actually we have our number of pods raising. This is from the Grafana, based on, if you remember, Prometheus stack. So Prometheus and Grafana as well, running within the cluster. I think that's it. And thank you for listening. If you don't mind, this is a little bit of a survey, 2 questions, just 2 ratings, and maybe some feedback that helps me and my company basically to fine-tune talks and understand if there are topics that are more appreciated than others. That's it. Thank you.
Thank you.